Hey everybody, we're going to do these vector notes here, and hopefully this time the video will be with the audio. We'll just see how well it works out for us. And vectors are going to be symbolized by an arrow, but they're quantities that have both magnitude and direction. So our first thing here is to learn how to turn on the little blue ink pad. And so we're going to put magnitude in. Magnitude is how big you are. For instance, if I was going 40 miles per hour, 40 miles per hour would be my magnitude. But vectors also have direction. And so, for instance, I'd have to say I was going 40 miles per hour north, let's say. So both magnitude and direction is what vectors have. Now they're going to be symbolized by an arrow. And so basically, anytime we see an arrow in physics, it's going to be some sort of vector. And the length isn't actually going to represent the magnitude. So the bigger the arrow is, the bigger the number that the vector is going to have. So for instance, a 40-mile-an-hour vector would be longer than a 10-mile-an-hour vector. And the angle is going to represent the direction. So that's why we're going to need the protractors and all that good stuff for... Why can't I get this thing to write very well? Okay, so magnitude and direction. Now, when two more component vectors are added together, they act as one vector called the resultant. And yeah, just draw this out for you real quick. So write down the word resultant, and then I'll draw it for you so you can see what's going on. So for instance, if I had a vector that was going to the east like this, and I add it to a vector that's going north, so if something's pushing to the east and something's pushing to the north, the actual resultant is going to be the object going northeast like this. So this would be my resultant. I'm going to put an R right there. Now, the resultant, though, can be broken down into horizontal and vertical components. So this would be the horizontal component, this component number 1 here, and the green line would be component number 2. And so let's fill that blank in with the word component, or not. There we go. Now, it's tricky when you're adding vectors like I just did. You got to make sure that the head of the vector is where the actual arrow is. So the head of the first component, so if you notice the head of that red component right there, this red arrow right there, that's head, was added to the tail of the second component, so the green's tail. So these two blanks are going to be head and tail. And then when you draw the resultant's tail, so if you look at that blue line up here, you can see the resultant's tail is added to the tail of the first component, and it's connected to the head of the last component. So components always go head to tail, but resultants go tail to tail, head to head. Okay, so here's the two heads meeting up here. Here's the two tails meeting right there, and this is the result. So let me show you how easy these things are as far as adding. So we're going to assume that 1 centimeter on this particular legend down here is equal to 10 miles per hour. And I have a plane flying 50 miles per hour east. And if you notice, I put this red arrow, or this red vector, going from 0 to 5. So that's going to represent a 50-mile-an-hour plane going east. It's pointing to the right, so east is going to be our right. It encounters a 20-mile-an-hour tailwind. So that's not a tall wind, that should be a tailwind right here. And so we can change this little word here to tail. And it's blowing east. Show the mathematical addition and draw the components. Well, once again, when we draw the components, we have to add the components head to tail. So I'm going to take the head of that red arrow there and add it to the blue tail. And so the blue was 2 centimeters long, the red was 5 centimeters long. And if you notice, when you add those two together, you would get a resultant. Well, the resultant is drawn from the tail of the first to the head of the last. So I'm going to put my black arrow over here that I already drew. And so I'm going to start, the black arrow is going to start on the red's tail and end up on the blue's head. and so therefore it's 7 centimeters long. And it's pointing to the right, which means it's going east. Now these are really, really easy. And to do these mathematically, it's simply that easy as well. You're just going to simply take the 50, which is positive because it's going east, plus the 20 miles per hour, which is positive because it's going east. And that's going to equal the plane actually going 70 miles per hour east. Okay, so really, really easy to do. Now, let's take a look down here where you have winds blowing the opposite directions of each other. So in number 4, I have a plane that's going 50 miles per hour east, but now the wind is going 20 miles per hour to the west. If you notice, I added this blue arrow. Once again, it's still 2 centimeters long, but I added it from the head of the red arrow, and I drew it back to the west, or to the left, because west is negative. And once again, I'm always adding these components head to tail. Well, when you add your resultant, the resultant is drawn from the tail of the first vector, so the tail of that red vector, to the head of the blue vector. So if you notice, I'm going to take this black arrow here. I'm going to start it at the tail of the red vector and draw it to the head of the blue vector. And if you notice, that black vector is 3 centimeters long. And so the way you do this mathematically, once again, is very, very easy. Let me erase all this real quick. So I'm going to take my 50 miles per hour. It's positive because it's going to the east. I'm going to add to that a negative 20 because the wind was blowing west at 20 miles per hour, and west is negative. And when you get 50 plus a negative 20, you get 30 miles per hour. But that's only part of the answer, because you also should have to say east. All right, let's keep rolling here. Okay, let's take a look now at number 3, I think is what it is, maybe something like that. But anyway, it's on the next page over. It says draw the vertical and horizontal components of this resultant. Well, the resultant's going diagonal, as you can see here. So the horizontal component, whoops, what just happened? Whoops, sorry, I think I just paused it. Did I? No, I don't guess I did. Anyway, the horizontal component is going to be however long that arrow is in the horizontal direction. And the vertical component is going to be however long that vector is in the vertical direction. So that's all you do to draw horizontal and vertical components. It's pretty easy. You could also draw them up here if you wanted to. I could take it and draw the opposite triangle. So I could put the blue line up here, and I could put the red line over here. But as long as the components are added head to tail, so if you notice right here, the head of the first component adds up to or matches up to the tail of the second component. But when you draw the resultant, you have to have 2 tails put together and 2 heads put together. Okay, so just make sure you're always drawing those correct, and you'll be in good shape. Okay. Now we're going to get into a little bit more difficult problems here, and because we're going to do these both graphically and trigonometrically. And so I'll have to teach a little trigonometry as we go along here. I got a boat traveling east at 20 miles an hour. So the very first thing I'm going to do is draw a 2 centimeter line going directly to the east. So that's what I do here. So if you notice, I drew a 2 centimeter red line going to the east. Now it encounters a river flowing 20 miles per hour, and I should have put down the fact that the river was going south. So let's put a little S there for south. Right? And so now I need to take my ruler stick and draw a 2 centimeter line going south. So I did that. So the blue line is the river, the red line is the boat. And it says draw the components of the blue and red, and then afterwards show the calculations using the trigonometric method. Well, I know that to get the resultant, I'm going to connect the tail of the first vector to the head of the last. And so if I come over here with my ruler stick, I can simply measure this thing. And put this down here real quick. And so when I come up and measure this line, it ends up being somewhere around, I don't know, maybe about a little under 3, maybe 2.8, 2.9, something like that. But sometimes you get a little bit on the lax side because you don't have your lines perfectly straight, and you'd also have to measure the. So I got 2.9 centimeters, which is going to be roughly 29 miles per hour. Well, shoot, I'll put 30. 29 miles per hour. And then you'd also need to know your angle that it's going to go at. And so I'm going to get my ruler out of the way here and bring my angle over. When you look at the angle here, it looks like it's about, gosh, it should be a 45-degree angle, but it looks like it's a little bit less than that. But I'm going to go ahead and put down 45 degrees just because I know it is. And so it's going to be 45 degrees, and it went east first, and then it went south. So I'm going to put south of east. So 45 degrees south of east. Well, now it says for us to show the trigonometric way of doing it. Well, to use trigonometry, oh my goodness sakes, I don't know where that came from. To use trigonometry, we simply have a right triangle here. So I'm going to take the formula for a right triangle, and so since I have a right triangle here, let's go ahead and just use the formulas for a right triangle. So I know that a squared plus b squared equals c squared. So if I want to know how fast that boat's going to be moving, I'm just going to simply take the square of every component. So c squared equals 20 squared plus 20 squared. And then to get just c, I'm going to take the square root of both of those. And so that means that c is the 28 miles per hour, which is roughly what we got before. Okay. Well, now we have to figure out what the angle was. Well, if you look at the triangle here, I know the adjacent side. So here's the adjacent side is my red side. And I also know the opposite side, which is my blue side here. And the trigonometric function that has both opposite and adjacent is tangent. And the tangent of the angle, that little symbol there is called theta. It means angle. And theta, or tangent, equals the opposite side divided by the adjacent side. Hopefully in math class you learn these different equations called SOHCAHTOA. So is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So it's sine, cosine, and tangent, otherwise known as SOHCAHTOA. And that's just sort of a new mnemonic device for remembering these things. Well, watch what I do here. If I want to find the angle that the boat's going, I'm going to say the angle is equal to the inverse tangent of opposite over adjacent. So let's plug in our numbers here. I'm going to take and put in my calculator tan to the -1. That's hitting second tan. Well, put your parentheses in there, and you're going to put 20 squared divided by 20 squared. I'm sorry, I just said squared. 20 divided by 20. Do not put the square in, guys. Do not put the square in. And that ends up giving you 45 degrees. Well, that's only part of it, though, because you also have to give me the direction. Well, if you notice, the red line went east first, and then the blue line went south. So this is 45 degrees south of east. Okay, on this last problem we're going to do for this video, number 10, we have to do it both graphically and trigonometrically. So I'm going to have 200 mile an hour plane that's going 45 degrees north of east. So I'm going to take my arrow here, and I'm going to draw a nice little arrow that's going 20 centimeters at 45 degrees. Let's see if I can get, okay, so there's my first 10. Let me double that. I'm going to go way, way up here above the lines. Okay, come back up here again and extend that on up here. So that's my 20 degrees is 20 miles, 20 centimeters, sorry, is roughly right there. And now what I have to do is, it's going to get a little tricky here. It now says that it encounters a 15 mile an hour wind. So I'm going to have a 1.5 centimeter line blowing 30 degrees south of west. Now, I want you to know something when I set up my protractor. Whatever the last direction I give here, that's where you put the 0 of the protractor. Hello, come on, 0. And whatever the first direction is, that's where you put the 90 of the protractor. So if you look down here, I got my 0 on east. I got my 90 on north, basically. It's a little funky here because the way I did it. Okay. Now what I have to do, I'm going to add the wind vector up here. I got to add the wind vector up here to this last arrow. Well, let's look what I have here. I'm going to put my 0 on west and my 90 on south, because west is the last direction and south is the first direction. So let me erase all this so you can sort of see where I put my protractor. I'm going to bring my protractor up here, and I'm going to flip it around. Okay, flip my protractor around, or not. Hello, there we go. I'm going to flip my protractor around up here. And so now I have the 0 on west and the 90 is on south. I'm going to put a little tick mark here next to 30 degrees. So that way I know where 30 degrees is. So this is 30 degrees right about there. Hello, there we go. It's 30 degrees. And I went west first and then went south of it. Well, now what I want to do is I want to get my ruler and I want to come up here. And I want to line my ruler right up next to that red line up there. Okay, so there's my, let's bring this down here a little bit. Put my ruler right there. This is so hard to do on a smartphone. Okay, now I'm going to draw now a 30-degree line that's a 1.5 centimeter line that's going to go from the end of that black line towards that little red line. I'm going to go ahead and make it red here. So let me get my 1.5 centimeter line. So that's one, looks like about right about there. Boy, that is lousy. Anyway, okay. Well, now what ends up happening here, let me go ahead and change that color for you. Hold on one second. Okay, so if you look real carefully, I have now a 1.5 centimeter line or vector going 30 degrees south of west. In fact, I think I have that not going south of west enough here. Let me bend that down a little bit here. It looks like it's going 20 degrees instead of, go back down towards 30. There you go. And there you go. So that's not about right. Okay. And I now have to draw my resultant. Well, my resultant's going to go from the tail of the first vector to the head of the last vector. So let me go ahead and start down here with my tail. Whoa, that's a dark line. Okay, that's going to look really, really dumb. Anyway, I'll change that in a second. But anyway, I'm taking this blue line. I'm going to go all the way up to the edge of that red line. Now, if you notice, the wind blew the plane off a little bit. And it doesn't really make that much difference until your airport's really, really far away. Then you could be really, really far off the runway. And so I'm going to change these vectors around. So hang on one second for me. Okay, so now I've changed the blue line a little bit here. Well, now if you want to find out where the plane's really going to go, we just take our protractor and bring it down here. I'm going to flip it around again and bring it down here, get it straight. And so if you notice, now the plane is actually going, instead of 45, it's actually looking like it's going somewhere around, if I move this over, probably around 47 degrees. Okay, so it's about 2 degrees off from where it was. And north of east. And now we've got to figure out how fast it's actually going to go. Well, the way you do that is simply taking your ruler and measuring the line. So let me bring my ruler over here now. Get that turned around over here. Start measuring. Let me get this all lined up here. So much easier with a real ruler. All right. And so now we're going to have, let's see, that's about 10. And so it's about there. So it looks like about 18 point something. And once again, you'll do it better with your own ruler. So I've got about 18, it's like about 0.4, something like that, centimeters. And so 18.4 centimeters would be the same thing as about 184 miles per hour. Now, the thing is, with all this ruler stuff, it gets really, really, really inaccurate. So there's much, much easier ways and much, much more accurate ways to do that using trigonometry, and that's what I want to show you next. All right, everybody, so in order to do this the more accurate way, what we're going to do is use trigonometry. And I'm not going to draw this the same way that I've been drawing all the other vectors real accurately as far as measuring it with a ruler and stuff. I'm just going to get a sort of a mental picture of this. And so I'm going to draw a little coordinate axis here. And I'm going to draw my plane here. And my plane's going to be in the red. And we said it was going 200 miles an hour. So I'm going to put a 200 here. And the angle that it was going to be 45 degrees north of east. So I'm just going to put a 45 in there. I also have a wind that's going 30 degrees south of west. So I'm just going to draw another angle down here. I'm not drawing the scale or anything. So this is south of west. And I'm going to put a 15 down here because it's going 15 miles an hour. Okay. Now, what I'm going to do is I'm going to divide all these resultants up into components. For instance, this 200-mile-an-hour airplane is actually going to the east this much, and the wind is blowing to the west this much, according to the blue line. Well, I could also say that the plane is going to the north this much in regards to the green line, and the wind is blowing to the south this much. Well, my whole mentality here is this. If I add up all the blue lines, it's going to tell me how much the wind or the plane is actually going to end up going. What's the resultant? If I add up all the green lines, it's going to tell me how much the plane's going to end up going in the north and south direction. So I'm going to make a little chart here. And let's start off with the blue lines. So let me make this over to blue. And I'm going to call that the X direction. So I got a little chart here, and I'm going to put a little X here. Okay. And I'm going to call this the vector of the plane. Instead of putting a vector, let's just put a P for plane. And so the plane in the X direction is blowing according to this blue line right here. And this blue line is the adjacent side. Everybody see that? Okay. Now the red side, that's going to be the hypotenuse. So I'm going to put a little h up here. Well, the trig function, the trigonometric function that we use when we are trying to find the adjacent side, and we know the hypotenuse, is the cosine. Because, there's all this thing up here. Because cosine of theta is equal to adjacent over hypotenuse. Well, if you want to find the adjacent side, which is how much the plane's going in the x direction, the adjacent side is equal to the cosine of theta times the hypotenuse. Okay, so all I did with there was cross and multiply. I took the cosine here and multiplied it with the hypotenuse there. Okay? So therefore, the plane in the x direction is actually going the cosine of 45, now make sure you're in degree mode on your calculator, times the hypotenuse, which is 200, and you end up getting an answer of 141.42. So that's how much the plane's actually going. Well, let's add that to how much the wind is actually going. Well, the wind is also blowing in the x direction, and this is the adjacent side. Okay. And so I'm going to use the same formula, the cosine, but this time it's 30 degrees times the hypotenuse of 15 degrees, not 15 degrees, but 15 miles an hour. So once again, cosine times hypotenuse still gives me the x direction. And when you put that together, you're going to end up getting a 12.99. But it's not positive, it's negative because the wind's blowing to the west or left. So if you want to find out how much the plane was actually going to go totally in the x direction, I'm going to call that the resultant. Okay? The resultant in the x direction is adding this 141 to the negative 12.99, and that gives you 128.43. Well, that's great that we know how much the plane is going in the x direction, but we also have to know how much it went in the y direction. So let's do the y direction, which is green. But now the y direction is the opposite side of that triangle. Same over here with the wind. Well, the trig function that we use when we want to find the opposite side, and you know the hypotenuse is not cosine, now it's sine, because the sine is opposite over hypotenuse. Okay, so I'm going to figure out how much the plane is going in the y direction. I'm going to figure out the opposite direction. I'm going to put a little O. That's not a zero. That's an O. Okay, and the formula is going to be the sine of theta times the hypotenuse. So let's put in those numbers. The sine of 45 times the hypotenuse of 200. And that gives me sort of the same answer I had before, which is 141.42. So the plane is going a positive 141.42 or north at 141.42 miles per hour. But you got to remember, it has the wind blowing against it. So let's figure out how much the wind's blowing in the y direction. So I'm going to take the sine of 30 times 15 miles per hour. That's a 30, not a 31. And so that means that the wind in the y direction is blowing 7.5, but it's not a positive because it's going south. So it's going to be a negative 7.5. And when you add the plane to the wind, you get a resultant y direction of 133.92. Well, you're still not done yet. We have actually two more steps to do. If I want to find out how much the plane is really going to go, if you combine the wind and where it's pointed together, let's take this resultant and sort of redraw it here. And so I went 128.43 in the x direction. So I'm going to redraw that line. I'm just going to put a 128.43 down here. I drew it going to the right because it's positive in the x direction. The resultant is also positive in the y direction. So I'm going to draw, adding it head to tail. I'm going to add a 133.92 going up. Well, that means the plane is actually going to end up going like this. It goes from the tail of the first to the head of the last, right? So let's figure out how much magnitude that red line would have by taking a squared plus b squared equals c squared. So a squared plus b squared equals c squared. That's a c squared. So c is equal to the square root of 128.43 squared plus 133.92 squared. Sorry about my bad handwriting. And so that means the plane is actually going to go 185 miles per hour, 0.56. 185.51 miles per hour. Now we got 184 when we did it the ruler way, so we weren't too far off. Now let's do one more. You also have to find the direction that's going off. With the ruler, we got about 47 degrees. Let's see what we get when we do trigonometry. Now, I want to find out what this angle is right here. Where's the plane actually going to be pointing when the wind blows against it? So I now know the opposite side is this green side. Here's the opposite side. I wish I could write that better. Sorry. The blue side is the adjacent side. Here's adjacent side here. And so the trig function that we use when we know opposite and adjacent is tangent. Remember SOHCAHTOA? So tangent of theta equals opposite over adjacent. Boy, my handwriting looks pathetic here. Look like I'm signing the cash register seat at Kroger. All right, so I'm going to take, in order to find the angle, I got to get that tan to the other side, so I'm going to take the inverse tangent. So you hit negative tan button. Well, the opposite side's the green, so that's 133.92. Golly, that looks horrible. And divide that by the adjacent side, which is 128.43. And the answer you get for your theta ends up being, I don't know, somewhere in the general vicinity of 46.2 degrees. And we got 47 when we did it with our protractor, so we weren't too far off. 46.2 degrees. Now watch this. The blue line went east first and then went north of it. So the way you say that is 46.2 degrees north of east. And that's all I got to say about that. Hope you enjoyed your 30-minute video. Sorry it was so long. Bye. Love you.